Hello reviewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about video game mesh. So let's dive deep into it. So what the heck is a mesh? Well, it's on a base level. You go deep in, as in like 1970s computer graphics. It is a basically vertex. It's a point. What is a vertex? Vertex is a point which has XYZ coordinate. Like you take a vertex, it has coordinate. You take another coordinate, it has coordinate. So that's how we start. We take a vertex, we start with that. Now you create two more. Now here's the interesting part. The moment you create three vertex, you can create a triangle, basically the smallest closed shape that you can build. So now you have a surface. Now that surface has a up and down, again a positive side and negative side. So that's how we start. That is the fundamental building block of anything 3D, be it VFX, be it GFX, be it whatever else have you. So that's how it starts. You start with a vertex, you create a triangle, and that's how you begin. That's why in video games we always count things in try count. What is the try count? Now generally try count looks ugly, so we generally use quads nowadays. So and again, there is no flaw in using pentagon or hexagon. It's just that quad is the most efficient. Triangle looks too ugly, quads are most efficient. Be mindful, from computer point of view, it's like if you make hexagon, it's still a triangle from its point of view. It's just lot of them, and it's just that we do not like the idea of re-triangulation. Because even if you make a like let's say a cube, from computer's point of view, computer is redrawing all those into triangles anyway. So computer redraws it. So you do not want to have oops, oh I thought it will fold like this, it folded something else. That's the reason why we generally want quads, not pentagons or hexagon. And if you ever had pentagon or hexagon in your mesh and you are a 3D game artist, you won't be a 3D game artist for no more, my man. Like missiles will be fired for you. So that's how we start. You take a vertex, it has a three-dimensional jota, you create a skin. That skin is made out of triangles, you keep extending it, and voila. Now you have a mesh. That's how it starts. Now you increase the number of vertices, number of triangles, and slowly you can add more and more detail. So this is what players plays with. Like whenever you think about 3D game, this is what they're interacting with. This is where everything happens. Player control, interaction, animation, decals, and everything centers around the mesh, generally the character mesh itself. So that's how it happens. Now here's the interesting part. The CPU load of these puppy are surprisingly low. For example, you may be like, okay, I went from 76 triangles to let's say 69,000 triangles. Would that be very heavy file? No. Ironically, no. Like this data is surprisingly easy to store. So it's not that heavy. However, while the oomph required, like the hard drive required for those puppies are not heavy, the CPU required to render those puppy is idiotically heavy, meaning it takes a lot of crunching power to actually render it and show it out. So it's one of those things that you have to be very mindful. You can increase try count as much as you want, but if you want a real-time rendering, yeah, you have to be very limited on that. And be mindful, that is the difference between a high-quality asset and low-quality asset, is the try count. You can texture your heart out. It will not make any difference if the try count is low. Like you cannot bypass this. This has to be done. So that's why you can see many games that have like community patches where people have made up resolution, the textures and all that, but does not look the right way. That's the primary reason. If the polygon mesh that is below the texture is not high enough, it's not going to look mesh. Like I've seen some like redone Crisis, and it's like it looks the same again to me, because I know what I'm looking at. I'm like, hey dude, it's a low poly, man. It's a low poly. You just put a high resolution texture in there. You have to make it high poly in order to flow as high poly. So higher polygons equals more quality, and in-game FPS is directly proportional to how much triangle count is being rendered in a single scene. You always want that puppy to be as low as possible. Like that directly affects your FPS, so to say. So you always like your target, you will have a target FPS. For example, most single player cinematic games type, let's say God of War or Horizon Zero Dawn, those will be targeted at 30 FPS. So they will keep increasing the try count until they reach that saturation. And then they'll tone it down a back. Then we'll get some even more toned down version 2 as a game artist, and it's like, okay, now you model it. So this is how we start with mesh. Then the first thing you do after a mesh is texturing. Now here's the deal. Mesh itself is nothing. Like if you look in from a computer's point of view, there is nothing. It's just like, okay, there are points. It's a point cloud to it. Yeah, it has a surface, but again, it has to show something on the surface. Let's say it just has a flat color. Okay, that's it. There is nothing to it. It does not look like metal. It does not look like plastic. It has nothing to it. So solve that, we utilize textures. Now, unwrapping is basically the simplest format. You take a three-dimensional data and you map it into two dimensions. You are basically unfolding it. Like if you are in India, we have a lot of what we call sweet boxes. So those boxes are literally open it up. It's just a flat paper. You can open it up into it's a paper box, so to say. So unwrapping is the same thing. You can take a character, unwrap it, and all you are doing is basically creating another data on that vertex. That like basically vertex in the games have far more data than xyz. So it also has one data that is xy coordinate only, not xyz, only x and y. So that vertex, let's say vertex number 35, will have xyz coordinate, but also have two extra coordinate that is for unwrap, where the heck that vertex is in the mesh. That's how it knows. Basically, you're taking 3D mesh, opening it up into 2-dimension. So now you can paint on it. Now, whatever texture file you have, computer knows where that file is supposed to be rendered. Basically, let's say you put red here. Where the heck red is supposed to show up in a mesh, it will use vertex counting, and then it's like, okay, that's where it's supposed to go. So that's how we start. Basically, you build your mesh, you unwrap that puppy, and then you paint on it. Now, there is a lot of things that goes into making feel out of it. Basically, how the heck skin feels like skin. Cloth feels like cloth. It takes a lot of things to give that feeling. Back in the days, we just used colors. We did not had the horsepower to do anything more. But nowadays, we do some more horsepower thing. For example, we'll start with color. It also called diffuse map, and then we'll add normal. Normal is generally you make a high poly mesh, and then you bake its normal. So it gives the feel. It's not high poly, but it will give the feel of high poly. So you start with color, normal, and then you have roughness, you have metalness. There is 10,000 more, but generally these are the four things you will have. So what is roughness and metalness? Well, imagine it this way. You have two things that are shiny. For example, eye that is shiny versus a metal pendant that is shiny. How the heck you will differentiate both of them? Introducing roughness and metalness. If you have metalness value of 1 and roughness value of 0, that means it's a metal. So rendering engine, basically the shader in that rendering engine will know that polygon which has value of in that coordinate will know this polygon is supposed to be shiny because it has that data. You could be completely opposite, like it's an eyeball. You can say metalness 0, roughness 0. Now it will be like a billiard ball, like a very shiny kind of thing. So that's how we map everything. So whenever you see black and white images in a 3D sense, those images are not just images. Those are basically you are mapping a bit value, basically 0 to 255. That bit value is translating into this level, like 0 to 1, you map into that. That's how shaders are working. So if you do not want to do that, like let's say you're modeling a rocket, you can just select it and make it metalness into 1. But if you really want it, sometimes you can see people like they have a decal and the decal is extra shiny. How will they make sure? They'll make sure that decal on a texture page has a different value. So that's what we do. That's what people have to do to give you that right feeling. So paint will have a different kind of feel. Soot, let's say you are modeling Falcon 9, you have soot. But soot supposed to be different. Then raw paint supposed to be a bit different. So soot would have a very different kind of, let's say you can have soot that does not have metal particles, but it has some sheen to it. You may be like, hey, what if roughness is like say 1, but metalness is like 4 or 5? You can paint it like a gray value. So we have normal, roughness, metalness, and many more. So we also use alpha channel for transparency, because when I said like once you make a polygon or a triangle, it's just a surface. So what if you want to sew a hole in that surface? You're like, okay, how will you do that? Well, alpha map is there. So somebody figured out it's like, hey, we already have xyz coordinate mapped to x and y. So what if we map pixel to that x and y in such a way that shader knows whether to render that pixel or not to render that pixel? So in comes alpha map. So alpha map generally is, if it's white, render. If it's black, let it go. Like let the ray tracing go. So it will not render. That's how you see leaves in video games. There is no leaf. It's just a polygon that has a leaf texture. And why you don't see its edges? Because alpha map. So that's how we solve that issue. Now that itself creates another hassle, is that alpha channel or even roughness, metalness, these are grayscale values. Your image storage file, whatever JPEG, PNG, Targa, all these puppies are tri-data, meaning RYG. Red, blue, green. So if you have red, blue, green and you are only storing one black and white value, it's wasteful. So because gaming industry is very thorough about memory spaces, is that we're gonna be like, hey, what if, like, it's old days we used to do this. It's like you have only 3 channels per image. So you have a PNG file, let's say. So normal map will consume all XYZ, as in like, red, blue, green. Then you have diffuse, which is color. Again, color requires RGB, okay. But what about alpha? Alpha only requires one. So what we'll do is create a RGB map that will be like, okay, red channel is alpha map. Roughness is stored in green channel. Specular highlights are stored in blue channel. That's how we can create it. So we literally used to pack a lot of monochromatic data into channels of a single image file. Now, like, why? Well, this reduces load on the loading side of things, meaning your shaders have to pull that data, right? That data has to be pulled. So that, where is that data? That data is either your CD, DVD, or Blu-ray, or your hard drive, or SSD. It requires to be pulled. So how do you reduce the load of that stage? Well, it's generally better to have one big file rather than multiple small ones. So that's why this RGB map file would be much easier to load versus if you have 3 of them. And not to mention, image files are generally designed for 3 channel data. So it's like, don't fight it, don't create a proprietary format, just use that efficiently. And heck, nowadays I don't even think, unless you have basically requirement of a alpha map, you can just have normal and diffuse. Use Targa file which have alpha channel, and in that you can have a specular and one you can have roughness. So you can have a complete rendered model with only 2 texture files. Now nowadays, again, I'm reasonably sure, I'm a bit old, like as in like 6-7 years ago I used to work on this. So now I'm pretty sure there must be a bit more extra texture sizes, but generally you only gonna have 3 image file. One image file would be like your color, one would be normal. Both of them could have alpha channels, both of them could have actual data on alpha channels, and then you'll have one another which will be like specular, alpha, or glow map. Sometimes glow maps are also used. So other than that, not much. So this is how we handle the texturing part. We have to be really precise with it. While I look at my VFX brothers and they're like, alpha is a file. I'm like, what the hell is this? Why alpha is a file? Like that's so painful. Like I had to spend time to learn how to do those. And these people are like, here's a file, alpha file. I'm like, what do you mean it's a file? How do you compress it and push it into like, no, it's just a file. I hate that. Then we come to the LOD. So far we have managed the 2 things. For example, we started to sort out mesh, we started to add texture to it, but here's the deal. Game is an interactive environment, meaning you can be close to it and you can get far out of it. For example, the object is close, now you can be far. So that creates an issue. It's like, if something is far away, let's say this is the viewport that is being rendered and you're talking about something, let's say a character is on top of a hill and let's say village is here, but it's only this size. That means only few thousand pixel, not even thousand, few hundred pixel is there that has to be rendered. But here's still, what if there's a village there? Okay, computer will try to render the whole village there. And it's like, dude, you're spending so much computational horsepower for a surface area that is so small. Basically, we have to be very mindful because if you do not do this, computer will render everything as far as it can see. And that's how VFX works. But here's the that's a wasteful rendering. Again, VFX has the luxury of just lol, but computers, because it has to run in real time, it does not have that luxury. So everything, if it's like, hey, if it's only consuming few pixels on your screen, don't waste time on it. So that's how we do it. So how do we achieve this? Well, we achieve by LODs, level of details. For example, if your character is interacting with it, let's say a car mesh could be 480k triangles, but character goes away a little bit. It could drop to 240. And here's the deal. What happens if you walk away from the surface area that is consuming on your screen goes down? So now not only your resolution requirement went down, the computation horsepower also went down. What if it walks away even further? Now it tricon drops to 120. What if even further? 60. Now again, this is a bit more extreme. Generally, we'll have much bigger jumps. So, and again, same thing is done with texture. So if the character is very close and you can see the detail, it will be like using 512 by 512. You zoom out a bit, it will just use 256 by 256. Zoom out even further, it will be like 128 by 128. That's how we make sure the whole scene is rendered and there is no blank blocks. And you can see this feeling in Google Maps. If you look into a corner and zoom in and you zoom out, you see like, hey, texture was there, but it's low resolution. Then you zoom into that part, it's like, okay, now I'm feeling with high resolution. Zoom out, but no matter, even if your connection drops, you can never zoom out so much that it will be like there is nothing. It will always have a low resolution map. It loads low resolution first, then it adds detail where you are zooming in. So that's the only way we can reduce CPU and GPU load. Your texture goes into GPU load goes down, that LODs reduces CPU load. Now you can have a whole scene where things are there, things are far apart, they are still there. That is very critical. For example, this is a box. Like you zoom out, the box should not disappear. Box should be there, but it should be like, hey, this is just a box, because again, it's consuming so much small area in the screen. It's like, hey, it's just a box. You zoom in, it's like, okay, now we have cross braces and all that. Again, this is a bit extreme. We in games, if we do our job right, you should never see that, like the swapping of low LODs and going away of LODs. You should not able to see that. Like it should always happen smoothly. Bit difficult to do, but you can see that in a new game, City Skylines. LOD swapping is not optimized yet, so it like looks very janky. So levers are made and swapping is done based on detail, distance, and that again requires in the calculation of the viewport engine. So LOD is also critical. Your mesh also has to become lighter, and texture also has to become lighter. And VFX guy, what do you mean it has to become lighter? What do you mean I have to remodel the same thing again and again? Then we come to the collision part. Now collision is basically, this is how your 3D becomes a 3D game. So collision is how your physics engine does anything in 3 dimensions. So far I've talked about 3 dimension, that is rendered, like things you see, like that's just light calculation. But how the heck you're gonna interact, how the heck you're gonna jump or do anything, those requires collision, or hitboxes sometimes they are called. So that calculation is idiotically expensive. Meaning if you think vertex are expensive, it's like, bro, no. If you like textures are expensive, no. Collisions, yes. Like collisions are so expensive that if you have a car mesh, a very high resolution car mesh, the collision would be like, hey, one box, bigger box, a smaller box, the end, go home. That's how expensive collision meshes are. Like you can have a mesh, like actual in-game mesh that has detail, gear teeth and all that. What will be the collision? The lowest polygon they can make, like the lowest what you call cylinder they can make, that still fits it. Like you can have a detailed chair, everything is smooth and butter, man, and then the mesh would be like just one block. Go ahead. Like it has to be done that way because it's very, very expensive. And the low res mesh is necessary for requirement, because again, it's not that physics does not allow you to calculate it. Computers can do it. It's just they do it in VFX industry. Do it in gaming, your FPS will go from 100 FPS to 0.00001 FPS. So it has to be done, and it has to be balanced with gameplay and interaction fidelity. For example, you can say, like this is exaggerated example, you have a mesh that looks like there is an opening, you fire your projectile into it, it bounces. Why it's bouncing? Well, it's bouncing from the collision mesh. You can see this whenever you are shooting in a shooting game. Again, hopefully modern games don't have this much issue, is that if you shoot through something that is curved and you shoot, like you will find decals in floating midair. So they are not floating in midair. Decals is being rendered on collision mesh, because collision mesh is the one that is calculating the physics. So whenever you pew it, it's like calculating the ray tracing of that. So ray tracing intersects with collision, collision detects it, collision puts a decal map. Now here's the deal. It does not know whether the collision is actually accurate to the mesh or not. We try our best, we try our best to make it accurate, but we cannot, because again, it has to be balanced. So yeah, it would be possible, like it's not impossible. It's possible to have collision that is very precise or very conformed to the gaming mesh, but there is a computational penalty to that. So it has to be balanced. Nowadays, if like this chair is done, we'll literally squash this. The geometry will be made like this. Back in the days, game engines did not even have that option. Like collision mesh were like just blocks, and somebody had to make the blocks. It cannot be any other shape than blocks. Nowadays we have a bit more oomph, bit more horsepower. So now you can have a bit more high resolution. So if you are in a shooting game and you are shooting like through blank air, it will actually go through. It won't be like, hey, randomly I hit something else. Recent Counter-Strike game has a lot of issues where they're like, dude, character, I'm shooting the character, but it's not registering because the collision mesh is offset. That happens. So this is a very, very computationally heavy thing. That's why like game interactions are so jaggedy, so to say. You're like, hey, I'm not touching this. Like only in cutscenes, everything looks like, whoa. But the moment you are playing the game, it's like, it looks like everything is floating, because again, everything has a floating mesh that's interacting with each other. If you ever have the luxury of seeing a game engine with basically collision mesh, turn on the collision mesh opacity, you will see, oh, everything is interacting so well. It's just that the low poly nature of it makes it low poly. But in VFX, they use main mesh as collision mesh. So in let's say VFX, if this chair has to roll over, the chair will do the collision map completely. It won't be like, oh, there is a box is rotating. It will like a chair that is falling over. Consequence, it will take hundreds of hours to render. So that's why collision happens. Then we come to the animation. Now, it's all about the flow, man, because here's this. So far, all you have is what looks into the scene, how you calculate it. But what happens? Well, animation happens. Whatever you are saying is generally animation, unless it's a ragdoll. Ragdoll is, again, it's an animation done by physics engine. So animation is what gives you the flow. What's it all about? Because without animation, there is no point to it. So character, generally, whenever you see a fighting character or other characters, they generally have a mesh like this. Now this mesh is for our viewing pleasure. It's not actually a mesh like that. It's just a vertex. It's just like if you look into a computer program, it will be like, hey, it's a vertex, and it will have some constraint, like, you know, let's say this vertex from this vertex, like the vertex that I put here, vertex I put here. In a character model, it will be like, okay, the distance has to be locked like this. It will not allow you to change the distance in game. Of course, when you're modeling it, you can change whatever you want. It's just that, and that will affect the shell around it, that mesh around it. So instead of rotating each vertex, you will be like, okay, I rigged it. Now the vertex that is ankle, this bone here, you will rotate it, and voila, this will happen. So this is what we call rigging. So once we rig it, and then the animators go, get into it and actually animate it. Even if you have motion capture, once you capture it, it has to go through so much manual process. At the other end, is more or less like a manually made thing. But it does have the signature. Artists do try their best to preserve the signature. So you will have scenes like this where it's like, character has some action, that action will be stored as, like, you know, kicking action, running action, falling down action. So all these actions had to be stored, and this is how we animate that if we are doing it completely manually. So assets, that's will happen with the character. So even speaking, mouth motion will be into animation set. But sometimes assets also, not sometimes, all the time, asset also get their own animation. For example, this I made long ago. So let's say if I'm sending this to game engine, it will be like, this is the game file, you open it up into your Unreal or Unity, it will be like opening, opened, closing, closed. So game will know, like if you go press E, right, whenever you see the interaction, it will do something like this. It will play that animation, then it will be in steady state. Sometimes in steady state there will be a little bit of motion, so it does not look too dead. So that's how we do it. So that's how the game system takes care of it. Game engine is the one that is deciding which animation to play. You just give it the data, it decides based on player input, based on the situation, based on the physics engine. It's like which animation layer to play. Now, how the heck VFX does? Now, this is the biggest difference between VFX and just basic stuff. It's like whenever we do in gaming, this is a very enhanced rig. Like nowadays, we have very advanced system. Basically, back in the old days, if you have a bone like this and you rotated your hand like this, it will rotate it. And you had so few vertex, it would not made it in a way, it will look ugly. But now we have sub bones. Basically, this will rotate, let's say 180. You go like this, it rotates 180. This will rotate, let's say half of that. This will even half. So there is a layers of it. Now that allows us to give a really good approximation of human skin animation, but it's like, it's, so how the heck VFX does that? Well, they render the whole damn thing, meaning there is actual bones there, actual muscles there. And now, of course, it's not rendered as in like nobody is texturing it. At best, they will put some default red color for muscle, default white color for bones, or may have some basic noise just to show, like, you know, it will help. Like that's the same reason why we are rendering this. It helps us to see, understand what is happening. Is that's how they are rendering. So whenever they fold their muscle, there is an interaction inside that is of geometries. Those are interacting, and that's you know, basically telling how the skin vertex should move. And benefit of that is like when you see Hulk in Avengers movie, it's like there is a lot of stuff there. Like his skin actually moves on top of muscle. How can you do that if there is no muscle? This system will not allow you to. That's the biggest difference between gaming animations and basically animation that you see in the movies. Sometimes what the, game companies will do, if they have to do a cutscene and it's like very up close and very personal, they will do all this, basically this thing, and they'll just save the vertex data. And that vertex will be placed on your character mesh in gameplay. It will look awesome, but you're like, hey, where is your facial detail? In cutscene, I saw so much facial detail. When I'm like playing, interacting, it's like, oh, everything would be like very base level. Why? This is difficult to do, but I do not think this can be done real time now. Again, which is ironic given the fact this is from an Unreal demo, but I do know it can be done. I think if you have 1490, RTX 1490 and running on like, you know, 14th gen Intel or something like that, you should be able to do it. It's just like games are designed for the lowest denominator. So the crappiest console that you can find, think of that. So that's how we do, like in game, like trust me. And if you are talking about Kung Fu Panda, trust me, they actually simulated the muscles, the bone structures, and fat, extra fat. That's how like his belly has to use doing like that. So there's a lot of simulation there. Like Godzilla, trust me, some engineers and artists sat down. It's like, how his bone should be, how his reaction. Of course, it won't be high fidelity as like this, like abs, but it will be there. Only then his scales will behave properly. Creature designs. You do not want to know how much effort it takes, like a designing of smog. It takes effort. I do respect this part of VFX artists. It's like I'll lose my mind if I have to like, wait a minute, I have to design bones, I have to shape them, I have to put muscles, I have to put some reaction to it. It's like, I'm out, man. So this is the animation side of things. So this was my presentation on basically video game mesh. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.